Welcome everyone to the last talk of today. We have the pleasure of having Tomasz Maszczyk talk about the title you have on the screen. Okay, so please.
Thank you for nice introduction. Pardon my French. My title is a shameless paraphrase of very well known. Doesn't work. Title by Marcel Proust, la recherche du temps perdu. Côté, chez Swan. Instead of time, my story will be about lost topology, lost notion of a space. And instead of one from Proust's novel, there will be Swan, who is an author of a well-known theorem about vector bundles as finite dimensional projective modules. So this is the content of my talk. First, I'm going to explain what is non-commutative topology from the modern point of view. The main tool of the subject is something which is called KK theory, which, however, is not sufficient to reproduce everything we know from algebraic topology, and we would like to repeat in non-commutative geometry, as you saw from Francesco's talk. Next, I will explain what exactly is missing here from classical topology in the realm of non-commutative geometry. And it will turn out that what is missing could be filled, in some sense, by studying non-commutative principle and associated vector bundles. Then I will show that using them, we can recreate some analog of the multiplicative K theory for non-commutative algebra. And finally, I will show even more abstract generalization of methods used to achieve this in terms of some categories. It is not expansion by in the void, because this abstract point of view simplifies all details of all computations, all considerings very much. Okay. So, what is non-commutative topology? So nowadays, it is simply KK theory. Okay. So the present state of the art of non-commutative topology consists of bivariant Kasparov's KK theory. The formal structure of the theory is that it is a triangulated category, which means that we are speaking about nonlinear objects in a way, to some extent, linearizing them, or making this category additive, at least. Objects are separable sister algebras, and for them, we can compute Z2-graded K-theory groups, and making this construction a functor on this category. This way of thinking is not restricted to non-commutative geometry, because in many branches of mathematics, people are doing very similar things. For instance, in algebraic geometry, people are talking about the category of motifs, which is the idea to make the category of spaces, Reich spaces, varieties, to some extent, additive category in which you could consider some analog of short exact sequences, which are distinguished triangles. sitting of my house. Also, in stable homotopy theory, people are considering category of suspension spectra. It is a very similar idea. Moreover, this KK theory restricts to metrizable locally compact Hausdorff space, although it is defined in terms of simple algebra. Then, by restricting them, this bivariant theory to algebras of continuous functions vanishing at infinity, or metrizable locally compact Hausdorff spaces, we can think about KK as a kind of bivariant theory of spaces in the classical case. And speaking about system algebras, we can think about them as non-commutative spaces. So the trick is very similar as Francesco did in his talk, by formal changing the orientation of all arrows in all diagrams. Okay. What is the common feature of all these additivization construction mathematics applied to geometric objects? They do not measure exactly what is expected to be the main subject of this geometric initial theory. For instance, stable homotopy equivalences do not recognize the plane homotopy type. It's a quite radical operation on the category of spaces, adding so many morphisms, which are very far from continuous maps between the spaces. Therefore, these spaces can be chopped into pieces which cannot be glued in the sense of topological space. They become something more complicated, less similar to the spaces that we expect, even less similar to homotopy types. The KK theory does the same. Even worse, there's a theorem, which is a consequence of the Rosenberg-Choquet theorem, that any two metrizable compact Hausdorff spaces whose K groups are abstractly isomorphic, and you saw in Francesco's talk how different could be spaces having the same abelian groups, even D2-graded abelian groups of K theory, they are already KK equivalent. So KK equivalence means simply an isomorphism in the KK category of the part. Okay?
So sorry, meaning that there is a plane map on the level of spaces which induces isomorphism
Yes.
at the level of KK.
I cannot see you, but I yes.
Adam Weger from
Yes,
Prague.
I recognize your voice. Yeah. Yes, because these generalized maps are rather correspondences than geometric maps between spaces. Okay? And the same example as Francesco showed you, if you consider the complex projective space of complex dimension n, it has the same K groups, abelian groups. Oh, my phone is okay. Okay, as Francesco said, for instance, in this case, one space has only one connected component, for instance, and another space consists of n+1 discrete points. Okay, but K theory, the abelian group of K theory is the same. So from the point of view of this theorem I showed you, Rosenberg-Schocker theorem, they are indistinguishable on the level of KK theorem. Okay. So, as Francesco already said, the idea is to use the following fact. If we have two compact space Hausdorff spaces, which are related by an honest geometric map, inducing homomorphism between K groups, then the existing multiplicative structure of a ring structure on this K theories are the structure is preserved by this induced map. Okay. Therefore, these K equivalents of metrizable compact Hausdorff spaces can be promoted to multiplicative K equivalences. And then the situation changes a lot, because in this category we have what Francesco was talking about, namely every space as every set is a natural comonoid. Okay, there are two structural maps. First is the constant map, okay, to the singleton or one-point space, and another map is a diagonal map. And this diagonal map, as you saw, can be used to create some product structure on this invariance. Okay. And now, what is happening in categories which do not mimic this geometric category of space? For instance, in algebraic geometry, this category of motifs we could create cohomology theories of many sorts, but all they are equipped with something which is called the cycle class map, which sends intersection products of. So actually, it's like taking the system of equations, and you remember that putting equations together means the intersection of sets of solutions. Okay, so this intersection product under this cycle class map goes to some multiplicative structure on the level of this cohomology theory, and this is very important. This stuff. Similarly, in the category of spectra in homotopy theory, in stable homotopy theory, this comonoid structure can be moved from the category of spaces, the category of spectra. Okay, and suspension spectrum functor puts everything. Preserves this comonoid structure because it's a strong monoidal function. Okay. So the argument now is different. Since every K equivalence in the classical situation must preserve this cup product, these can distinguish not plain abelian group structure from K theory, but can distinguish this multiplicative structure, the ring structure. Okay, and you can see two rings when one ring has lots of nilpotents. Okay, another one is it's a product of copies of Z. So they are, from the algebraic point of view, they are very, very different. Okay. This multiplicative structure can be used not only to distinguish space. There are some problems which can be solved using this. For instance, for n greater than 1, this product, which I will call cup product, although the word cup product is reserved for some construction in singular homology or similar cohomology theories, but I will use it even to some extraordinary cohomology theories. Okay, so for instance, for n greater than 1, we can have a hyperplane, projective hyperplane, CPN -1, inside of the complex projective plane or space CPN, and we can show that there is no retraction from this bigger space to the capital. And it is clear that if you understand that mapping K groups cannot be equivalent to mapping K rings, the reason is that mapping K groups, having a map between K groups, abelian group homomorphism, in general doesn't imply the existence of a mapping between K theory rings. What is peculiar about this product? So on the level of K theory, people love this construction because it's very robust, okay, for many respects. However, K products are, although they are more sensitive, they distinguish more things. They can be used to do things which are impossible on the level of K theory. They are also more fragile than the plain abelian group structure, which means that, for instance, in the category of motifs, if we have morphisms in this category coming from correspondences, then these correspondences typically do not preserve the K product. They destroy K products. However, sometimes they destroy it in a quite interesting way. For instance, there are some birational transformations which are called stratified Mokai flops. These are correspondences which do not respect K product. However, correction terms can be expressed by very interesting invariants, which are called Gromov-Witten invariants. Okay, so the situation, since this invariant, this kind of invariant is very deep, very, very difficult, it means that the way in which these correspondences destroy this multiplicative structure is related to very deep things. All these cohomology theories I meant satisfy the Mayer-Vittori's principle. As Francesco explained to you, Mayer-Vittori's principle is a way of inductive computation of invariants, okay? Provided you are controlling the way of passing from one skeleton to the next skeleton. If you control these maps, gluing maps, you can compute this cohomology as it was shown before by Francesco. So this suggests that maybe there would be possible to construct some invariant which doesn't require this very restrictive property of classical spaces, which is possessing this diagonal mapping, but still general enough to mimic the construction of this multiplicative theory on the level of non-commutative spaces. So there's a proposition of a definition. Following Eilenberg, MacLean, we are introducing some graded version of their object they defined, which we call augmented ring. In a slightly more general meaning. Every augmented ring is a triple consisting of a ring a module over this ring and a distinguished element in this module, okay, satisfying the following conditions. This ring is a Z2 graded unitary ring. M is a Z2 graded R module containing this distinguished element of degree 0. And a morphism of such triples consists of a unitary Z2 graded ring map between these rings, and then a unitary Z2 graded S module map between these modules. So by this ring homomorphism from S to R, we can think about M as an S module. And then we can relate these two S modules by some Z2 graded S module map. And this map is supposed to preserve or transform the distinguished element of this module into another distinguished module of another module. Okay. So
Can I ask?
Yes,
what do you mean by unitary? Is there some star structure?
No.
Unitary S
Yeah,
module
in
map.
algebra, people say that something is unitary if it preserves unity.
Oh, okay.
Maybe unital would be
Thank you.
more proper for this audience. Okay, and then one could ask, what's the relation between these augmented rings and rings? So first of all, we have a functor from rings to augmented rings, repeating this ring, so taking this ring itself as a module over itself, and distinguishing the unit of this ring as the distinguished element of this module. Okay. It turns out that this map is a full embedding, a full faithful functor, okay, but quite special because it admits a right adjoint. In such a situation, if we have a full embedding onto some subcategory, okay, and this embedding admits such a right adjoint, then this right adjoint is called a co-reflector. Okay, and we can say then that this subcategory is a co-reflective subcategory. Okay, so rings inside of augmented rings is a co-reflective subcategory. Okay, and this co-reflector can be written in terms of very obvious, very simple association to every triple Rm and the distinguished unit-like element. We forget about M and this unit. So look what is happening in these two directions, because you have functors in both directions. In one direction, we repeat the ring. Okay, so we're creating this module M, which is R itself. In the opposite direction, we are forgetting about this module part and the distinguished element. Okay, and the situation of two categories, one subcategory, full subcategory of another, making this subcategory co-reflective. This situation is very important. You probably know from non-commutative geometry, because compact spaces, regarded as a special sister algebras, form a co-reflective category, subcategory in compact quantum spaces. And even this right adjoint, the co-reflector functor, can be easily understood. It is the space of classical points. Okay, which means the space of characters, the homomorphisms of a given sister algebra to the field of complex numbers. The second question, what one could ask, is how these augmented rings are related to abelian groups. If we want to forget about this multiplicative structure, and instead of speaking about the multiplicative K invariant, we want to speak about the plain abelian group valued K theory, then we have to compare this category with abelian Z2-graded groups. And now we have a functor which uses this module part. So this is very important. This is not like forgetting the ring structure on the level of R. It's taking this module part, okay, and we are forgetting the module structure over this ring. Okay? And these two functors, this full embedding and this forgetful functor to abelian groups, form the following commutative triangle. Everything works as it should be. Okay. And then, if we have a, let's say, compact space, then to every compact space, with every compact space, we can associate a triple consisting of K theory, its copy when you forget about multiplication, but you remember about the module structure over itself, and equipped with a distinguished element, which is the class of one-dimensional trivial module, okay, over the algebra of continuous functions. And this association extends by functoriality of the K ring uniquely to a contravariant functor from spaces to augmented rings. But this association is fairly trivial. We are taking, it is built with K theory. So what is this path about? The point is that in a non-commutative situation, this language allows us to modify this choice which we make for classical spaces in a way which, restricted to classical spaces, reproduces something which reduces to K theory. So it's a very good thing because it's something that is called a correspondence principle in physics. Then if we embed our classical situation in our more complicated quantum situation, then this classical aspect survives inside of this quantum context. Okay. So what is the justification for this new terminology, this new construction? Is the following theorem. We proved with Francesco that there exists a full embedding, which we call Q, which must refer somehow, this should ring a bell, okay, in your memory about quantization. So Q means something, passing to some non-commutative realm of CW Waldhausen categories. So this is the notion you know from Francesco's talk. And a functor K, red, K, such that the following diagram commutes. So what do we have in this diagram? So we have compact Hausdorff spaces, classical compact Hausdorff spaces. We have the functor of K theory taking values in the category of Z2-graded rings. Okay. These Z2-graded rings can be embedded into augmented Z2-graded rings. So these are black arrows. And we complete the pair of these black arrows by this red part of this diagram, consisting of embedding of compact Hausdorff spaces into some special category, which we call K compact quantum spaces, where K means that it will be, the object will be equipped with some additional structure. And from this category, there will be another K functor taking values in augmented Z2-graded rings. Okay. This diagram is commutative. If we speak about the CW Waldhausen category structure, in both categories, cofibrations are monomorphisms, and weak equivalences are K equivalences. Okay. Moreover, the composition of this red K with this forgetful functor from augmented rings to abelian groups factors through K theory of unitary system algebra. So what's the moral meaning of this theorem? On the level of classical spaces, we change nothing. On the level of non-commutative spaces, after forgetting some details, we are coming back to classical K theory, taking values in Z2 graded abelian groups. Okay. So this means that this red K functor is really an enhancement of this classical K theory and reproduces the usual K theory of system algebra. So now, what is this K in front of this K compact quantum space? Okay. The main idea consists in the following slogan. The slogan is to measure non-triviality of the topology of a space by invariance of associated vector bundles. So let me remind you what is classically this theory about and how this is related to measuring non-triviality of topology. Namely, if we have some compact principal G bundle and we are interested how much it is non-trivial, we can consider some constructions, which is called the associated vector bundle construction, to go from these principal bundles to vector bundles, or even to K theory, and then computing invariance of this associated vector bundle, we can check whether this invariant is trivial or not. If this invariant is non-trivial, then this means that original principal G bundle was non-trivial. So it can be used to measure non-triviality of topology of our base of this principal vibration, because you know that if the base of the principal G bundle is contractible, then all principal G bundles must be trivial. Okay. What about these associated vector bundles? They have the following property. They all are pullbacks of some universal construction. It's a universal vector bundle which lives on some universal kind of base of some universal principal G bundle. And every bundle, vector bundle over some arbitrary base, compact base, can be achieved as a pullback of this universal one via some so-called classifying map. And this is the consequence of the compatibility of two operations, of the operation of taking or constructing the associated vector bundle and the operation of taking the pullback of this vector bundle. Okay. So classically, this construction is like this. So I have to explain here some symbols. So consider a space X, which is a right G space, the set of orbits of a free G action on X is called X mod G, and the same. So this is the base of this principal bundle. Okay, while X should be regarded as a total space of the G bundle. So if I have another G bundle, X prime, over its base X prime mod G, then having something defined over X prime, provided these two G spaces are related by a G equivalent map, I can construct the following pullback. So this pullback is achieved in 2 steps. So the first step is a base change, replacing this base x mod g by the new base x prime mod g. Okay? And after some associativity of parentheses in this formula, we get that this construction is the same as the pullback afforded by the induced map of bases induced from this original equivariant map. Okay. And it turns out that this very simple construction allows us to describe very big chunk of topology in terms of things which are related to representation, theory of representation of these structural groups of these principal bundles. For instance, the theorem which Francesco presented, no, Francesco didn't present. The context of this theorem was presented in Francesco's talk. It's about the standard filtration by skeleton, by hyperplanes in the complex projective space. On the level of K-theory, induces a tower of standard nilpotent ring extension. Okay? Every K-theory of every skeleton can be identified with the ring of truncated polynomial. And every map between this K-theory of skeleton is simply reduction modulo lower and lower powers of this variable x. And this variable x can be very easily described. It's a first, it is an element in K-theory corresponding to the associated vector bundle where with identity subtracted when the representation used to associate this vector bundle with some principal bundle comes from the fact that over this complex projective space you have always a sphere, okay, whose quotient by the action of the circle gives you this complex projective space. Okay, so everything in this topological picture depends on the representation theory of U1 and the action of U1, the free action of U1 on odd dimensional spheres.
But it didn't say which representation.
So this is identity representation. You have U1 can be identified with invertible complex numbers fitting in complex numbers. It's a one-dimensional representation. So this line bundle leads to this generator of this K-theory ring. Okay, so it is not a strange thing that this representation theory of U1 is so powerful in this case, because this filtration by skeleton, they are approximations of the classifying space of the group U1, which is the infinite complex projective space. So because of this universal nature of this construction, everything depends on the representation theory of U1.
And the CP infinity is not locally compact.
No. Direct limit construction. Okay. If you think about vector bundle, then you can speak about their invariants. And the most important invariant of vector bundles, or their K-theoretical classes, is the Chern character. To be prepared for this non-commutative generalization, we have to think about families of G principal bundles, because in this non-commutative situation, instead of having one principal bundle, we are speaking about some family of deformations. Okay, so this deformation space is parameterized by this parameter Q, for instance. Okay, and then we have the following picture. So on the left-hand side, we have the natural transformation on this universal level. It's a Chern character from K-theory of the classifying space of this group G, going to some kind of cohomology. If you prefer, it could be the RAM cohomology for in the smooth case. It could be singular cohomology in purely topological case. Okay, and the same transformation makes sense for every space. Okay, and even you could put this Chern character into family parameterized by some space S. Okay, and then such a diagram, which is commutative, reflects the fact that this construction is natural in the sense of the category theorem. Okay, so it's a natural transformations by of two functors, and these natural transformations are also related by induced maps. So this is natural. Okay, so this map CL is what I meant before, this classifying map, pulling back this universal thing to this concrete thing over a fixed base. Okay. So computation of this result on the level of cohomology of the action of this classifying map is quite difficult in general. But in simple cases, there are some recipes. Namely, we can find some convenient models up to homotopy equivalence of this classifying space BG, or we could replace this classifying space BG by some more algebraic object whose cohomology computes the cohomology of this classifying space. Okay, and then we can compute the effect of this classifying space on the level of cohomology. Okay. Now, in the non-commutative geometry, we take a different path. For instance, let's assume for a while that our group is a linear algebraic group. Okay. This is equipped with an action, a joint action of this group on itself. Okay. And the coordinate algebra of this an algebraic G variety, and its coordinate algebra multiplication or group law of this group induces the structure of a coalgebra on the coordinate algebra of polynomial functions on this algebraic variety. Okay, and since everything is ad invariant, we can look at ad invariant part of this coalgebra. Okay, this part invariant with respect to the action of G on itself by conjugations. Elements of this are called sometimes class functions. Okay, and from this, I will show you how to pass to something you probably know from differential geometry, which is called Chern-Weil map. So first of all, this algebra of polynomial functions admits a filtration by powers of the ideal, which is the kernel of evaluation at the neutral element. Okay, and since neutral element is invariant with respect to the joint action, it's obvious that this filtration is G invariant. Okay, then with this filtration we can associate the graded associated module. by summing up consecutive quotient of this filtration and taking the G invariant part. Okay. So now we are using the fact that G is reductive or compact, whatever you wish. Okay. But then, since this linear algebraic group is a smooth variety, these quotients can be computed as powers of a quotient of the type M mod M squared, okay? Which is nothing else but the linear space of linear functionals on the Lie algebra of this algebraic group. Okay, so we end up with G invariant polynomial functions on the Lie algebra of this group. Okay, and probably you are familiar with the classical theorem of classical Chern-Weil map from differential geometry. The latter object, first of all, being an infinitesimal counterpart of this, what we started with, it is a domain of the classical Chern-Weil map. Okay, using this, we can compute the effect of this classifying map on the level of cohomology. Okay, so this starting point for our analysis, our constructing of this invariant, has some precedent in mathematics, namely replacing the Lie algebra, which is an infinitesimal object, by the space of G acted on by itself by conjugations, plays a fundamental role in the construction of something that is called G equivalent cyclic homology of block-Gershon. So if we expect at some moment that cyclic homology will appear as a recipient of this invariant, a very natural choice. Okay. So this example is showing how we can prove non-triviality of some principal bundles using this computation, using the Chern character applied to this associated vector bundle. For instance, if we know that this tautological quaternionic line bundle over HP1, the quaternionic projective line, which is diffeomorphic to S4, is non-trivial, then this implies non-triviality of all Hopf fibration, quaternionic Hopf fibration. Okay, so now how to go from the classical picture to non-commutative. So our aim is to generalize this reasoning to the non-commutative setting by using the following principles. So first of all, of course, we start with Gelsfand-Neimark regarding compact causal spaces as commutative unitary system algebra. Next, we are using Peter Weil principle, saying that every compact group is determined uniquely by its Hopf algebra of representative functions. And then we apply the principle, which generalizes this Peter Weil observation, this theorem, to the context of compact principal bundles. Now, not only groups, quantum groups, compact groups itself. Thanks to the Baumann-Hayas Peter Weil version for compact principal bundles, we can think about principal bundles as commodule algebras over the Hopf algebra of representative functions.
There should also be Kenny the Comer.
Kenny the Comer. Sorry, Kenny. Well, he's not listening. Okay. Then, of course, we are applying these principles to our beloved finitely generated projective modules, coming as module sections of topological vector bundles. Okay, and finally, we are using Baum, Hayas, Mattes, Szymański. I hope everybody honored here, saying that associated vector bundles can be regarded as associated finitely generated projective modules using the Milnor-Moore cotensor product with respect to this coaction of this Hopf algebra of representative functions. Okay, However, there are some problems with this program. What are they? So first of all, although every classical vector bundle is associated with a principal bundle, namely the principal bundle of unitary frames of this vector bundle, such construction, such association is at least elusive in the case of non-commutative geometry. Nobody succeeded in constructing an analog of a principal, non-commutative principal bundle of frames for a given finite generator projective model. The same about local triviality. This principle of local triviality, this notion of local triviality is lacking in non-commutative geometry. We can do something in terms of Piotr could speak about by hours about this approach of mimicking these properties of locally trivial things by means of some the partitions of unity described in some open covering. This could be extracted in terms of some maps, but not on the level of the space itself, but on the level of some cone over this space. So this is some analog, some extent mimicking this situation of local triviality, but in the context of locally trivial vector bundles or principal bundles, it's not a complete replacement. Even worse, for some non-commutative algebras, and this is the point important for the point of view of the subject of this conference, there are some algebras which started, in fact, all theory of or algebraic version of theory of algebras associated with graphs. So Leavitt algebras, a pure algebraic counterpart of theta.
Kunz algebra.
Sorry?
Leavitt algebra is just Kunz algebra.
Yeah, this special one,
Yeah.
yes, constructed for Leavitt to show that there are non-commutative algebras for which it is impossible to define even a rank of a free module, because finite generated free modules over this algebra could be isomorphic even if they are they have different exponents.
Yeah.
Okay. So this means that we cannot speak even about triviality of finite generated projective modules. So we can say that even that our given non-commutative vector bundle is trivial. So how we can use then these bundles as to measure non-trivial topology of our quantum space? So it's a problem. And there are many more problems, despite the fact that some aspects of classical topology could be reproduced on the level of non-commutative spaces, but some other aspects of classical topology completely disappear, dissolve, when we want to forget about commutativity.
Mike, may I ask you a really difficult question?
Yes.
So you have in 55 minutes of your talk, you used less than half of your slides.
Yes. So
How do you tend to play
I
it?
have to speed.
Well, I mean, speeding up is not an answer. I mean, you have less than half of your slides in 55 minutes, so we'll not sit another hour.
Okay. So, what are non-commutative principal and associative vector bundles? So, as I told you, the situation depends on some coalgebra. Remember, this coalgebra is a generalization of the coalgebra of these polynomial functions on this linear algebraic group. Then we have the action, principal action of this coalgebra on algebra A. P is the coaction invariant subalgebra. And then we see that if we have algebra with the principal coaction of this coalgebra, and B prime is it's a collection invariant subalgebra, then any equivariant collinear algebra homomorphism from A to A prime induces an algebra homomorphism between these invariants. And if we have a finite dimensional representation of C, this Eilenberg-Moore cotensor product denoted by this square produces an associated finite dimensional projective module over B. Okay, and we call this the section module of the associated non-commutative vector bundle. Okay, so now what is important? In this level of generality, we have a very similar principle saying that association commutes with pullbacks when pullbacks and association are meant in a proper way. Okay, in particular, every equivariant star homomorphism between these commodal algebras induces a map on the level of K-theorem. Okay, and this is described by terms of a very simple recipe. Okay, so it calculates the effect of this induced map on the level of K-theorem is calculated essentially from representation theorem. Okay, so then we can repeat this Chern-Weil computation, okay, which can be summed up by a similar commuting square with different objects and different arrows, but it's obvious then we have to think about co-representation of this coalgebra as K0 of this classifying space, some kind of classifying space. And there is a canonical map from these co-representations to some elements of this coalgebra, which essentially are traces. Okay, so this trace chi is in fact a character of this universal associated principal vector bundles over this classifying space. Okay, so I will omit rephrasing the same more complicated way. One way. Okay, so maybe the last is important. In this square, we have a diagonal composite, and this diagonal composite was already known before we started with not considering this. Piotr, together with Tomasz Brzeziński, defined Chern-Galois character. So, in a sense, you can speak about this diagram as some twofold decomposition of this Chern-Galois character. Okay. So I will omit what interesting constructions are behind this invariant. Anyway, we end up with some analogy between the Chern character and the composition of the Chern character by means of the construction of relating the algebra B with the algebra of infinite matrices with entries in B, in which projections could be regarded, or classes of these projections could be regarded as elements representing elements of K-theorem. And then on the level of this construction of these infinite matrices, this Chern character can be described as a kind of tautology. So we found another tautological description on the left-hand side of our diagram, and you see complete symmetry. Behind this symmetry, there is some abstract approach which uses some generalized character. So now, how to go from classical topology to K topology? So we start from a notion of a family of group actions. So we do not assume from the scratch that we are talking about principal bundle. We have two practically arbitrary actions, even of different groups over different spaces. But these two actions should be related by some commutative square. Okay. In this situation, we have some canonical map relating these two constructions. So the left-hand side, like this, it's a quotient of the product U prime cross G with respect to the diagonal action of G prime on both factors. On the right-hand side, we have a fiber product. Okay, and there's an obvious formula for this map, and we call that this morphism of two actions is Cartesian if this canonical map here is an isomorph. It turns out that a big chunk of equivariant topology can be rephrased in terms of this construction. So first of all, for orbit spaces, we can create a similar diagram. We can compute a similar, more canonical morphism. And then we see that for this morphism to be an isomorphism is equivalent for Q to be a quotient map onto the space of orbit. Okay. Next, the problem of slices. If you have an action, again, we can rephrase this in the form of such a similar diagram. And then our canonical map being isomorphism means existence of something which is called a slice map. Okay. Also, principal bundles can be described entirely in this language. You need another diagram, and then you obtain another canonical map. And this canonical map is a graph of this action of the structural group.
Graph in a different sense.
Graph of the action. Further in this subject. Okay. This isomorphism is sometimes called the Galois condition, okay, which is tantamount to the fact that it's a principal G-band. Everything is classical. Okay. Change of the structure group. So in particular, the restriction or extension of the structural group or a principal bundle also can be produced with a similar diagram with the same condition. The canonical map being invertible here means that one principal bundle is obtained from another by the restriction, or in the opposite way, by the extension of the structural group. And finally, for locally trivial principal bundles, we have the following principle. Every morphism between locally trivial principal bundles is Cartesian in this sense. Okay? And among all these 5 examples, only the last one cannot be generalized to this non-commutative setting entirely in the language of something which is called facially flat Hopf-Galois extension. Okay, and this last one motivated us to take this as a part of the structure and axiomatize it as a search for the structure in which we could take this as a definition of a Cartesian morphism between non-commutative principal bundles. And this leads to the notion of K-topology. So K-topology consists of the notion of K-covering family. It's a construction which mimics some kind of topology introduced by Grothendieck and by geometry when he starts from some covering families satisfying some properties. So our K-covering family is a compact quantum space of a compact quantum space. It's a compact quantum principal bundle with a compact quantum structure group G. So we regard principal G bundles as covers of this topology. Okay, and then K topology is a collection of K covering families satisfying some properties. And when we have this K topology on X, then we call this X K compact quantum space. So it's an extra structure.
Sorry, what's the difference between DAM and AM? Have definition.
Oh, sorry. So A means Francesco all the time. D is Andre. Sorry. Yeah. Okay.
Tomasz, you really have to wind it up.
Yeah. So this language of this K topology allows us to speak about K-continuous maps. Not every star homomorphism between star algebras coming from representation theory should be regarded as a continuous map in this sense. There are two, on one hand, there are too many star homomorphisms having nothing to do with continuity in any sense, because non-commutativity introduces some dynamical structure, okay, like in quantum mechanics. Okay? So these system algebras are not in fact the space; they are, morally speaking, stacks. Okay, or could be represented in the classical situation. There are analogs of some kind of spaces represented by groupoids. Okay, so you are familiar with this idea from today's lecture. Okay, so the K-continuous map is a map preserved, compatible with this K topology in an only possible way. Okay, if you think about the definition of a continuous map in terms of coverings, open coverings, this is verbatim, almost verbatim the same. Okay. Essentially, it's about the fact that the preimage of an open covering is an open covering. And this must satisfy some additional property of being Cartesian for this square, which means that it's a kind of full. So it means that the preimage, fullback of this covering, open covering is an open covering, something like this. And then, if we forget about K topology, we are coming back to the category of compact quantum spaces, which means that it's an additional structure. Mm-hmm. And what we get, so first of all, on the classical level, first of all, any J equivalent continuous map of locally trivial G principal bundles over the same base is an isomorphism. Okay. Second, any continuous map between bases pulls back principal bundles and leads to an equivariant map of principal bundles. So it creates this kind of Cartesian square. And finally, every continuous map is K-continuous with respect to K topology consisting of all classical locally trivial compact principal bundles. So in the classical situation, we lose nothing. We are adding nothing. We reproduce classical topology. Okay, but this makes sense also in this non-commutative situation. And this K topology, one could ask why I'm calling this topology at all. Because of the following theorem, that the families of compact quantum principal bundles, together with K continuous maps, form a coverage in the sense of Johnston. Okay? So the Johnston introduced the notion of coverage, which is a weakening of Grothendieck topology, but which is sufficient for speaking about at least sheaves, which is very important for algebraic geometry and topology. So this is our solution to this problem. Final point is about that this K topology allows us to create multiplicative K theorem. It is based on the fact that associated vector bundles are not only one-sided modules, right? They are bimodules. And being bimodules, they can be regarded as operations on K theorem. Okay? So we are taking the abelian valued K theorem as a module over this associated vector bundles. So this makes K theory a module over the representation ring of a given group G for every G, applying some conditions. Okay. And then we are constructing our triple in the following way. It will be a functor from K compact quantum spaces, taking values in augmented G2 graded rings, associating with this compact quantum space X. First of all, a ring, which is the inverse limit over all possible compact quantum principal bundles. Okay. of the system of quotients of the representation ring of the group, quantum group G, divided by the annihilator of this distinguished element, this unit-like distinguished element of this model. And so this is the even part of this construction, and we create this odd part by applying the same construction to the unreduced suspension of this space. And then using many things like both periodicity, non-commutative joint construction of Baum. No. Who are also Ludin Dobrowski. We are proving that M is a module. So R of X is a Z2 graded ring, and M is a module. So it's a triple of kind I was talking about. Okay. And then in this language, we could revisit this situation Francesco showing about these two non-commutative kinds of filtration by skeleton of complex projective spaces. So one is strict. It's about Waxman-Seubermann complex projective spaces. And we reproduce this Atiyah-Todd result. We can compute these rings corresponding to this multiplicative K-theory, and these are on the nose, these truncated polynomials. Okay. Similarly, if we do the same in this weak version, so now the correction is T from Teplin, but this means H or Hegel, theorem. And we obtained something similar. And if you remember that these two filtrations are related by equivalence, then this means that although they are not isomorphic, they should be regarded as a quantization of the classical K-theory type of CPN. Okay? So this means that quantization is not a how to say univalent operation. Okay, you can quantize things in many ways. So it's astonishing that going in completely different worlds of quantum construction, quantum deformation, we obtain things which are related by this K equivalence. Okay, so they are computing the same. So this unique object, this should be regarded as quantization of topology. Okay, not the single deformation. Okay. Okay, so I have to speak this higher category perspective. It's the language of proofs. What makes so I'm skipping. Fun. Thank you very much.
Thank you very much. I don't believe we have time for questions. Are there?
They are clapping.
They're clapping on Zoom.
Okay. So let's thank the speaker again.
Yeah.
Thank you. Thank you.
Thank you very much.
Very important.
And this closes today's session. Thank you.
Thank you. Bye-bye.
Bye.
Thank you, Adam. Why didn't you ask any question?